Okay, good day. So today we're going to discuss the LTE system architecture. I think most of us are familiar with the LTE system architecture that is currently um, evolving the way on how we do mobile communications technology. So this topic will deals with the overview of LTE system architecture, and the same way we're going to consider the architecture for this type of technology. So let me go forward. So this is the overview or the outline of the topic that we're going to discuss. So we will have LTE system architecture overview. At the same time, we're going to discuss LTE radio architecture, and then we will have LTE evolve packet core architecture. Together, we were going to discuss the barriers in terms of this kind of technology. And lastly, we will have the LTE control architecture. For the LTE system architecture overview, actually, LTE system architecture can be split into three domains. Those domains are access, evolved packet core or EPC, and the control, as shown in the figure. This figure reveals that access contains only one network element, which is the so-called evolved node B. Okay, so basically the main reason for this simplified architecture is to reduce what we call the complexity, latency, and cost, while we're going to increase the data throughput, which we're going to discuss also in this topic. So basically, the EPC consists basically of three functional elements. So the first one is the MME. MME stands for Mobility Management Entity, which is resides in our control plane of the EPC. So basically, the MME can be seen as an evolution of the serving GPRS support node, or what we call the SGS and control plane function in the general packet radio system, or the GPRS. The serving gateway SGW, which is in place on this part, correlates with the SGS and user plane function in the GPRS. So, all user plane packets in our uplink and downlink are traversing through our SGW, and the SGW will also act as a local mobility anchor that is able to forward the packets during the handover. For the PDN gateway, PGW, we're going to consider that it is the Global Internet Protocol, or the IP, mobility anchor point comparable to the gateway GPRS support node interface. So, the PGW will also contains the policy and charging enforcement function for the detection of service data flows, policy enforcement, and flow base. So for the control domain, it also contains three building blocks: the IMS, the home subscriber server, or the HSS, and the policy changing rule function, or the PCRF. The IMS further contains the number of functional elements which are required to control voice sessions, while the HSS is the main data storage for all subscriber and service related data of the IMS. EPC and access, the PCRF acts as bridge between the IMS and the EPC. Okay? For example, setting up required EPC barrier for a new voice session will required through the PCRF. So that's how these three domains work on each other. Okay, so again, the LTE system architecture were split into these three functional domain: the access domain, the EPC or the evolved packet core, and the control domain. Okay, and so as I was saying a while ago, for the first domain, the access domain, in the previous third generation partnership project 3GPP radio architectures, two network elements were defined: First, Node B and the Radio Network Controller RNC in the UTMS Terrestrial Radio Access Network or UTRAN. And second, the Base Transceiver Station BTS and Base Station Controller BSC in the GSM Edge Radio Access Network, or as we all know as the GERAN. The access domain contains only one network called eNode B. The main reason for this simplified architecture were again to reduce complexity, latency, and cost while increasing the data throughput and signaling rate. For the second domain, eBulk Packet Core domain, EPC contains three functional elements. In example, Mobility Management Entity MME, Serving Gateway SGW, and the PDN Gateway PGW. Under the Mobility Management Entity MME, basically this resides in the control plane of the EPC. The main function of this is to perform user authentication, mobility management, such as paging tracking area list or TAL management, and handover management, and EPS bearer management. While the Serving Gateway or the SGW, which is also resides in the user plane of the EPC, main role is to traverse by all user plane packets in uplink and downlink. It is also act as a local mobility anchor that is able to forward packets during handover. How about the PDN gateway or the PGW? What is the role of the PDN gateway? So it resides in the user plane of our EPC. The Global Internet Protocol or the IP Mobility Anchor Points allocates IP addresses to user equipments or the UE. And it also provides the interface towards packet data networks, PDNs, like the IP Multimedia Subsystem IMS and the Internet. It also contains the Policy and Charging Enforcement Function, PCEF, for the detection of service data flow fallacy enforcement, including discarding of packets and flow-based charging. So these elements under eBulk Packets Core domains plays an important role on how this kind of domain will secure the LTE system architecture on its given functions. Then for our second domain, the control domain actually contains three building blocks: the IP multimedia subsystems or the IMS, the home subscriber server or the HSS, and the policy and charging rules functions or the PCRF. Let's talk about each of those building blocks. For the IMS, it contains the number of functional elements which are required to control voice session. At the same time, overlay architecture to provide the LTE networks with multimedia services such as voice over IP or the VoIP, video conferencing, and so on. For the HSS, the main data storage for all subscriber and service-related data of the IMS, EPC, and access are stored here. And for the policy and charging rules function, it actually acts as a bridge between our IMS and EPC domains. Again, for example, setting up required EPC barrier for a new voice session. Okay, for the LTE radio architecture. The LTE radio access network, known as eBulk UMTS Terrestrial Radio Access Network or the EUTRAN, is constituted only with evolved node B or the eNode B. So this figure represents the LTE architecture, which is actually based on the principle of a single box radio architecture. The classical controller-based architecture has evolved to the all-in BTS radio architecture, which was also introduced as an alternative architecture in HSPA. Now, if we're going to analyze, the key driver was to enable easy scalability of the network as traffic increases, coupled with the separate handling of control and user data in the core network side. So as shown in the given figure,
The use of flat architecture also enables short latency and fast signaling exchange since all radio level signaling is only between the UE and the E node B. Also shown in this architecture, in order to facilitate radio resource management and especially mobility, there is an X2 interface between the E node B and the UE. Okay? This interface carries the necessary signaling to enable to exchange information on the radio resource usage between our base station to provide handover command when user is moving or to handle the data forwarding. So the functions of eNode B here are as follow. Radio resource management, in example, radio bearer management, handover control management, and all forms of radio control. Encryptions of user data packets, selection of MME, routing of user data packets toward SGW, transmission and scheduling of paging data. So these are the content of our LTE radio architecture. NAS stands for Network Access Straight to, RRC is for our radio resource control, PDCP is for our packet data convergence protocol, RLC is for radio link control, and our MAC or our MAC for our medium access control. And for our LTE protocol stacks, in LTE system architectures, all related protocol which include both user plane protocol terminates in the E node B. NAS signaling being non-radio signaling terminates in MME. So this diagram shows the function of the user data protocols as well as the control plane protocol stack. So they have their own responsibilities and functions in our LTO radio architecture. And then for continuation, in LTO radio protocol, we have to consider the following elements: the radio resource control, packet data convergence protocol, radio link control RLC, and the medium access control MAC. What are the function of those elements? First, for the radio resource control, it handles all necessary control signaling for the radio operations, including measurements control and handover commands. While the PDCP covers ciphering, which is form of security, and also IP header compressions. This is an important function of the PDCP. Use of header compressions is not mandatory, but quite essential in order to achieve good voice capacity, as otherwise the IP header overhead takes quite a large part of the capacity in the case of large amount of voice user. While on the other hand, RLC controls retransmission though this is not normally used for voice. Also, it controls the segmentation on the part of the networks. While for the MAC, as we all know, MAC is responsible for mapping and multiplexing of logical channels to transport channels, as well as taking care of the physical layer retransmission, which can be also applied to BOLTE due to the load delay operations. Now, the scheduling functionality with priority handling is also seen as MAC layer functionality, thus ensuring the LTE user or the BOLTE user do not have too much delay but can have high priority in the scheduler operations in case of congestion situations. Then, for the physical layer covers the channel encoding and decoding, error detections, and actual physical layer packet combining modulation or demodulation, and many other procedures for power control and multi-antenna operations. Also, bases on the orthogonal frequency division multiple access or the OFDMA for downlink and single carrier frequency division multiple access or the SCFDMA in the uplink is also handled by the physical layer. The main reason is to ensure both simple terminal receiver and power efficient terminal power amplifier operations while it reach the high capacity. Okay.
How about LTE Evolved Packet Core Architecture? So, this slide will talk about how the LTE Evolved Packet Core Architecture functions. Okay. So, the EPC is an evolution of the General Packet Radio System, or the GPRS. So, what's the function of GPRS? Where do we use our GPRS? So, basically, GPRS is used for mobile data services. Given the concession, the first packet switch PS mobile data service introduced in the European Telecommunication Standard Institute, or the ETSI 3GPP, release 97. In GPRS, there is a dedicated core for our packet switch data service. This dedicated core will serve the GPRS support node, or the SGSN, together with the gateway GPRS support node, or the GGSN. So this diagram shows how the G3GPP release 8 reference architectures work on. So let's consider, or let's discuss this given flow or architecture. For the PS core in GPR, it is used for global system for mobile communication, or the GSM, and UMTS access technologies. Then, EPC is used for GSM, UMTS, LTE, and non-3GPP access technologies to provide IP connectivity and service continuity in mobile networks. MME can be seen as an evolution of the SGSN control plane function in GPRS, while the serving gateway SGW associates with the SGSN user plane function in GPRS. Otherwise, the PDN gateway, or the PGW, is the Global Internet Protocol, or IP mobility anchor point equivalent to the Gateway GPRS Support Node, or GGSN, in GPRS. Okay, so this is where the EPC, or the Evolved Packet Core, is located in the given architecture. So this explains the role of the PS core in GPRS and EPC. Then for the mobility management entity, or the MME, in the LTE Evolved Packet Core architecture, the main control and management entity for mobility in a LTE network is the main role of our MME. At the same time, it keeps track of state and mobility of our UEs that are registered on the network. Okay? And also, it acts as a gatekeeper, handling user requests for network access, setting up and tearing down data sessions. At the same time, handles the authentication of users on the network, as well as basic authorization, which includes the function that the MME communicates with the home subscriber server, or the HSS, to get security information for authenticating the UE, and that the UE can authenticate the network as well. And then it also selects what SGW and PGW will be used for a given sessions. The primary responsibility of MME are as follows. First, Evolved Mobility Management, EMM, which deals with keeping track of UE's location and state, and Evolved Session Management, ESM, which deals with creating an actual data sessions. Then for the mobility management entity, as we continue, there are some other tasks that are being handled by the MME, which includes the following: NAS signaling and security, session and mobility management, including the intra-LTE and the intra-3GPP mobility functions, and paging control and execution of the UE, together with tracking area list management, inter-CN node signaling, roaming, which include SCA towards home SSS, and low pool interception for signaling traffic. How about the role of the serving gateway, or SGW? So the responsibility of SGW are as follows. First, user plane gateway for LTE radio network in inter-E node B handovers, and user plane gateway for inter-3GPP mobility, thus terminating S4, which is the interface between the SGSN and SGW, and relaying the traffic between 2G or 3G system and PD and GW. Also, a single UE can be served
by only one SGW at any one time. So the SGW anchors the user on that given scenario. And then it also receives the instruction from the MME to set up and tear down sessions for AUE. Also, it handles user IP packets between the PGW and the eNode B, which also acts as a middleman for signaling between the PGW and MME, as well as functionality. SGW is an IP router which or with support for a mobile specific tunneling protocol or GTP. And then some other tasks that can also handled by the SGW. First, assist the eNode B during inter-eNode B handover, which is also known as data forwarding. Second, downlink packet buffering and initiations of triggering for paging idle mode UEs. Then, transport level downlink and uplink packet marking. Lawful interception for roaming, and lastly, charging for data roaming. Then let's proceed with the function of the Packet Data Network Gateway or the PGW. The PGW provides a UE with access to external packet data networks. In example, Internet and IP multimedia subsystems by assigning an IP address to user equipment. And functionality wise, PGW is an IP routing and forwarding entity. Now, if the condition is if a UE has multiple data sessions to multiple PDNs, the UE can be connected to multiple PGWs. Some other tasks but which are also handled by the PGW includes barrier management, policy and charging enforcement functions or PCEF, accounting and offline or online charging support for data, packet filtering, optionally deep packet inspection, low pool interception, and user plane anchor for mobility between 3GPP and non-3GPP access systems. Now, how about interfaces and protocols in the EPC? So this is also an important role or important thing that we need to understand about LTE, about packet core architecture. Considering those interfaces, let's start first with S11. So S11 or S11 defined for the control plane between our MME and SGW. It also uses GTPC protocol to provide a GTP tunnel per user. Then for the S5 interface, S5 interface defined for the control plane and user plane between SGW and PGW. It also uses GTPU protocol to provide a GTP tunnel per barrier for the user plane, as well as uses GTPC protocol to provide a GTP tunnel per user for the control plane. While the SG1 interface defined for the control and user plane between PGW and PDN. At the same time, it uses IP packet forwarding protocol in the user plane and uses DHCP and radius diameter protocol in the control plane. Let's now further discuss the packet data network PDN connections via IMS and internet. Actually, there's an additional default barriers with a new IP address is created when services are offered via multiple access point names or the APN. So looking on the given diagram, for example, if UE gets PDN connections to IMS during the initial attachment, but when the user starts web browsing, the UE initiates another PDN connection to internet APN. Additional default barriers are always initiated by the UE request and removed by the UE or network. This figure actually shows an example where UE has two simultaneous PDN connections. One is for IMS and the other for the internet. Let's take note that the different APNs may be supported by different PGWs. For example, the IMS APN might be supported only in the limited number of PGWs, whereas the Internet APN might be supported in all the PGWs here. Barriers in LTE. Barrier is actually a logical packet transmission path set up at a UE, eNode B, SGW, and PGW. In LTE, end-to-end barriers are realized by the EPS barrier, which are collections of radio, S1, and S5, S8 barriers. At the same time, the EPS barrier identity is allocated by the MME and is the one that carries the information. Usually, it carries the user data. So this explains the barriers in LTE. So we have the radio, S1, S5, S8, and the GI connections here. Okay. For the ERAB, barrier is the combinations of radio barrier and S1 barrier. Okay, so this is where the ERAB is located. And then external barriers connects EPS barrier to external networks or external barriers. It works as the SGI interface. Now, how about the IP multimedia subsystems or IMS? IMS was originally intended to be the voice signaling and delivery platform for IP-capable network such as Universal Mobile Telecommunication Systems and LTE. It also provides the service for voice and multimedia over a packet switch network, as well as developed by the G3GPP organization to support IP-based multimedia sessions. So this is where the IMS is located. Okay, so again, it is intended for the voice signaling and delivery, okay, for IP capable networks. And IMS core is based on session initiation protocol, SIP, and real-time transport protocol or RTP. SIP is used to create and control sessions, and SIP functions work on call server control functions, CSCF, which plays an important role in IMS authentication. And devices can register their presence with the IMS network, receive messaging based on specific events types they subscribe to, and initiates and receive real-time multimedia sessions, which includes voice session, video session, and so on. Now, considering the main entities in IMS, so this includes call session control function, CSCF, application server, home subscriber server or the HSS, and then the policy charging rule function. So these are the elements of our IP multimedia system or IMS. So considering the call session control function, it includes proxy call session control function, service call session control functions, and interrogating call session control functions. Now, how does the proxy call session control function works? First, it is actually the first contact point for users within the IMS. All SIP signal traffic from the UE will be sent to the PCSCF, and it includes 5 unique tasks assigned for the PCSCF. So, what are those 5 unique tasks? We have the SIP compression, IPsec security association, interaction with PCRF, control of the network address translator or NAT, and emergency session detections. For interrogating call session control function, ICSF, there are 3 main tasks assigned for the ICSCF. So, which includes obtaining the name of the next hop, either SCSCF or AS from the HSS, assigning an SCSCF based on received capability from the HSS, and routing incoming requests further to an assigned SCSCF or the AS. Now, serving call session control functions includes the focal point of the IMS, and then as we going to discuss the responsibility of it actually handling registration process,
making routing decisions, maintaining session states, and it is responsible for storing the service profiles. Then, on the home subscriber server side, HSS, it actually acts as a database of subscriber information. Then, that can be inquired by MMEs to determine permitted services and holds the primary security key information for all SIM cards in a mobile network. HSS has the information that what MME in what network a SIM is registered on and can inform the old MME. Lastly, policy and changing rule functions or the PCRF is responsible for creating and tearing down voice barriers. It also acts as a bridge between IMS and EPC domain. Given an example, setting up required EPC barriers for a new voice session. So this sum up the architecture of the LTE. Okay, so uh this in this explain how each of those element performs their functions together so that they can perform the complete LTE system architecture. So thank you.